The big lie, dark matter. For most of modern cosmology, dark matter has been treated like a silent foundation stone. It's invisible, undetectable, untouchable, and yet we tell ourselves the entire universe depends on it. But what if this cornerstone was never really there? What if it was just a patch, a mathematical crutch we used to make our theories of gravity and motion line up with what our telescopes were showing us? That question, once whispered inside conferences and coffee breaks, is now being asked out loud again. Let's rewind to why the concept existed in the first place. It started as pure necessity. Astronomers in the early 20th century realized that galaxies weren't behaving correctly. They spun too fast. The stars in their outer arms should have been flying off into space under the laws of Newton and Einstein, yet they stayed bound. The math didn't work. Something invisible had to be holding them together, some hidden mass. That invisible something became the simplest fix, call it dark matter. It wasn't a discovery so much as a declaration that there was a hole in our understanding. Think of it like this. You're assembling a car, you start the engine, and it moves twice as fast as the horsepower says it should. Instead of questioning the engine design, you assume there's some invisible turbocharger hidden deep inside. That's basically how cosmology handled the galaxies. Physicists didn't want to throw out their equations. They wanted them to stay true everywhere. So dark matter became the turbocharger we couldn't see but needed to make the numbers work. Once that idea entered the scene, it stuck fast. By the 198s and 199s, every simulation of the universe's large-scale structure included oceans of invisible matter. The cosmic web, the interconnected network of galaxies stretched across billions of light years, was drawn on the assumption that most of what exists can't be seen. Dark matter wasn't just accepted. It became the scaffolding holding modern cosmology together. Students learned it as fact. Textbooks showed neatly colored diagrams of halos of invisible matter wrapping around galaxies. Even pop culture turned dark matter into its own brand of mystery, the unseen glue of the cosmos. Here's what's easy to forget. Dark matter was never directly measured. It was inferred. The whole idea rests on how visible objects move. When galaxies rotate more quickly than they should, that's considered evidence. When galaxy clusters lens light more strongly than their visible mass allows, we say the missing gravity must come from dark matter. Each observation was an indirect fingerprint rather than a body found at the crime scene. And that's where the problem starts. Indirect fingerprints can point in many directions. The motions and light distortions might just as easily hint that our understanding of gravity fails on massive scales instead of proving some invisible substance exists. But once you've cemented a concept into every equation and model, questioning it becomes career-threatening. For decades, anyone who criticized dark matter risked being dismissed as fringe. Still, objections have quietly grown. Many simulation teams admitted off record that models were being adjusted to match observed galaxies. It wasn't fraud, it was pragmatism. Theoretical physicists would alter the distribution of dark matter, tweak its behavior in ways that were never measured, until the computer-generated universe looked like the one we see through telescopes. Those small accommodations added up until the invisible matter had more flexibility than any known substance in physics. It could be cold, hot, particulate, diffuse, clumpy, or smooth, whatever the data of the day demanded. In other words, dark matter became not a single hypothesis but a moving target. The irony is that the better our technology got, the more sharply its absence showed. Scientists built exquisite detectors to find particles that could make up this hidden mass. They looked for WIMPs, weakly interacting massive particles, that might occasionally collide with atomic nuclei. They hunted Axions, ghostly ultralight particles emerging from quantum theory. They even stretched into the realm of sterile neutrinos, hypothetical cousins of the known neutrinos that would only announce themselves by gravity's pull. Every search came up empty. Yet the search went on, year after year, generation after generation. Because to admit that nothing might be there would mean reconsidering the very frameworks that unify general relativity, particle physics, and cosmology. How do you undo that kind of foundation once every scientific building sits on top of it? The narrative held strong. It must be out there, we just haven't looked hard enough. There's a fascinating psychology in that. A theory that predicts invisible matter when that matter isn't found doesn't get weakened, it gets strengthened. The logic becomes circular. The fact that we can't find it merely proves how elusive it is. And because each failed experiment can be explained away with a new variation, the concept keeps regenerating, immune to falsification. Here's the subtle consequence. When researchers run a universe simulation today, they can effectively paint in the missing mass wherever needed. If galaxies form too quickly, they dial back the clumping rate of dark matter. If they form too slowly, they dial it up. That flexibility lets cosmologists explain nearly anything, which feels powerful, but it also risks turning science into storytelling. A model that can fit any data set doesn't necessarily describe reality. It describes adaptability. And yet, to be fair, dark matter does a remarkable job at first glance. The pattern of galaxy clustering, the fluctuations seen in the cosmic microwave background, the scaffolding of the large-scale universe, all of these seem to line up beautifully when you include invisible matter in the equations. Whole fields of cosmology rely on that consistency. It's what makes the modern lambda-cold dark matter model, lambdictum, the reigning framework. Take away dark matter and the equations start to wobble. Galaxy formation accelerates too slowly. The web of the cosmos frays. Clusters no longer hold together in simulations. So you see the dilemma. The model works because we told it to, but the foundation remains imaginary. It's as if we constructed the entire edifice of astrophysics on a coordinate system that happens to fit observations, without ever confirming that its 0 point is real. When a Nobel Laureate criticizes dark matter today, they're not just questioning one hypothesis, they're shaking the scaffolding of half a century of work. You can sense the defensiveness this provokes among mainstream physicists. The immediate response tends to be, but it explains so much, and that's true, it does. Yet explanation isn't proof. The Ptolemaic model explained planetary motion for centuries with intricate circles within circles. It worked, until a simpler truth replaced it. History rarely remembers how comforting an old theory felt before it fell. Let's talk about overconfidence. Early cosmologists were careful, almost humble about this invisible ingredient. They said, "We think something unseen is adding mass." But as the decades passed and the evidence for particles never emerged, that caution evaporated. Textbooks started presenting dark matter as simply the majority of matter in the universe. It wasn't framed as a hypothesis anymore. It was a fact students were expected to recite. That jump from possibility to certainty happened not because of new evidence, but because repeating the same model over and over in simulations gave it inertia. By the 200s, papers began to speak of refining the nature of dark matter rather than testing whether it existed. Even failure to detect it became another data point for refining what it could be. And the deeper experiments dug underground, the quieter those refinements became, almost like whispers in an echo chamber. There's a reason some physicists started calling it the big lie. Not because of deception in the malicious sense, but because of how easily belief becomes convention, and convention hardens into doctrine. The same process has happened across scientific history. Once an assumption enters the core of a model, removing it means rewriting everything. So most people choose not to remove it. Look closely at high-resolution astrophysical simulations from the past decade. They're stunning, galaxies forming, merging, and swirling through a filamentary cosmos. But every pixel you see there depends on how someone coded dark matter's behavior. Those halos surrounding galaxies, they exist in equations, not in experiments. When the data doesn't match reality, like when dwarf galaxies rotate differently than expected, the model just introduces new complexities. Maybe dark matter interacts with itself. Maybe it's warm instead of cold. The beauty of theory is that it's infinitely adjustable. But this flexibility backfires. Observations from telescopes like JWST and surveys like Euclid are now precise enough that the wiggle room is vanishing. Entire galaxies have been found whose dynamics suggest there's little to no dark matter inside them. Others appear to contain far more gravitational influence than any plausible halo could explain. These mismatched systems act like anomalies feeding on anomaly, cracks forming in the walls of a theory that once seemed untouchable. And each crack invites the same quiet question. What if the gravity law itself is wrong? What if our whole reasoning chain inverted the problem from the start? That possibility, rewriting gravity instead of inventing invisible mass, was precisely what physicist Mordechai Milgram tried to explore with MOND, short for Modified Newtonian Dynamics. Back in the 198s, his idea was largely brushed off as fringe because it challenged the orthodoxy. But recent data hint that he might have been on to something subtle but real. We'll get deeper into MOND soon, but for now, note the irony. It predicts galaxy rotation curves astonishingly well without adding any dark matter at all. It just tweaks how gravity behaves at extremely low accelerations. And maybe that's the uncomfortable truth. Cosmology clung to dark matter not out of evidence but because of simplicity. It preserved the existing laws. Admitting gravity might need rewriting would mean thinking from scratch across relativity, quantum theory, and the entire cosmic timeline. That's a far heavier lift than blaming an invisible ingredient. Some researchers today call dark matter a conceptual stop sign. When equations don't add up, they write D for dark density and move on. It ends inquiry rather than beginning it. One astrophysicist compared it to software engineers adding a patch to buggy code instead of rewriting the faulty core function. The patch keeps the program running until the bugs multiply. The truly remarkable part is that the deeper we look into the cosmic web, the more the universe seems to defy simplification. Galaxies don't move like neat Newtonian wheels. They whisper strange patterns hinting at something deeper. And maybe those patterns aren't telling us about missing matter at all. Maybe they're revealing the wrinkles in space-time itself that we haven't yet accounted for. Dark matter might not be a lie in the moral sense. It's a placeholder for mystery. But the danger lies in forgetting that placeholders aren't permanent. They're meant to be replaced when we learn more. Now, a century after its inception, we seem to have run out of excuses for why this invisible mass refuses to show itself. Decades of expensive detectors, kilometers of shielding, mountains carved out for experiments, and silence. It's the cosmic version of calling an empty room haunted, because every creak sounds like proof. Still, the institution of science doesn't pivot easily. Billions in research funding, thousands of careers, and every cosmological database are tied to the dark matter assumption. To abandon it feels reckless, but to keep defending it, even as evidence collapses around the edges, is starting to look equally reckless. So maybe this is where the big lie label truly fits, not in deliberate deception, but in collective self-reassurance. The community convinced itself that the unknown was known because uncertainty is exhausting. After all, saying, "We don't know what 85% of the universe is," doesn't make for a comforting lecture slide. Calling it dark matter sounds much more professional. And now, as Nobel Laureates step forward questioning its reality, the narrative tension has reached breaking point. They're asking what should have been asked from the start. If the only reason we believe in something is because our math demands it, are we measuring the universe, or just our equations? To understand how this all began, how a mathematical necessity turned into cosmic dogma, we have to trace the origin story itself. The clues lie with a maverick astronomer nearly a century ago, noticing galaxies doing the impossible. That's where the dark matter myth ignited, and where we'll find its first cracks. The missing evidence. Here's what most people don't realize. The hunt for dark matter hasn't been a small side project. It's been one of the largest, longest-running scientific efforts in human history, a search carried out inside mountains, on the ocean floor, even in orbit around Earth. For 40 years, hundreds of experiments have tried to catch even the faintest whisper of this invisible substance. Yet every time detectors have listened, the universe has replied with silence. Let's start with what scientists thought they were looking for. If galaxies move faster than their visible mass can explain, maybe there are particles out there, massive ones, that barely interact with normal matter. They would be everywhere, passing through us right now by the trillions, but slipping through atoms without a trace. Physicists called them WIMPs, weakly interacting massive particles. The term became a kind of talisman. Find a WIMP, and you'd solve the cosmic mystery. You'd finally prove what 85% of the universe is made of. To catch one, researchers built detectors that almost sound like science fiction. Picture underground caverns lined with pure liquid xenon, cooled to near absolute zero. The idea was simple. If a WIMP collided with a xenon atom, it might make the atom recoil, and that tiny jolt would flash as a pulse of light. Experiments like LUX, Xenon 1T, Pandex, and later LZ were designed for incredible sensitivity, so refined that they could detect a single particle hitting once a month. If dark matter was real and created from WIMPs, those detectors should have lit up decades ago. But they didn't. One by one, each new iteration pushed the limits further, expanded the detection volume, filtered out cosmic background noise, and still found nothing. When results stayed empty, the theory didn't shrink, it stretched. Maybe the particles were lighter, maybe heavier, maybe they didn't interact with xenon at all, maybe with sodium or germanium. So new detectors were built with new materials, and they too reported silence. It became a pattern. No matter how we tuned the experiment, the universe stayed mute. Eventually, people started wondering whether the silence itself was telling us something. If WIMPs exist, why haven't we seen even statistical hints? By the mid-2010s, the parameter space, the map of energy ranges where WIMPs might hide, was nearly exhausted. The absence of results began to corner the theory, so attention shifted to other possibilities: axions, sterile neutrinos, supersymmetry candidates hiding in the quantum foam. Axions were the next favorite, theoretical featherweight particles predicted initially to solve a different problem in particle physics. Early proponents said they could behave collectively, forming vast invisible clouds around galaxies. Researchers built resonant microwave cavities, hoping passing axions would nudge photons just enough to reveal themselves as faint signals. The machines were tuned with exquisite precision. Still, flat lines. Sterile neutrinos followed, whisper-thin cousins of known neutrinos that interact only through gravity. Astronomers searched for their fingerprints in X-ray emissions from galaxies and clusters. A mysterious 3.5 keV signal once hinted they might be there, but further analysis diluted the excitement. Once again, no consistent signature appeared. Billions of dollars in funding, thousands of careers, decades of technology, and still the night sky refuses to give up a single particle. There's a growing unease about what this might mean. Because in science, repeated non-detection isn't just bad luck. Eventually, it's information. It says we might be looking for the wrong thing. Here's where the philosophical discomfort creeps in. The prevailing cosmological model, lambdictum, needs dark matter to work. Without those invisible particles, the entire structure of galaxies, clusters, and early universe formation collapses. So the absence of evidence threatens far more than one theory. It threatens the gravitational foundation of modern cosmology itself. That's why the community keeps searching rather than stepping back. Because the alternative, that gravity behaves differently on cosmic scales, rewires everything from relativity to quantum field theory. If you were a physicist whose entire discipline depends on stable constants, which would you prefer? An invisible substance that keeps the math neat, or the possibility that the universe rewrites Newton and Einstein every time acceleration drops below a threshold too tiny to test on Earth? But data doesn't care about preference. And recently, the inconsistencies have become impossible to ignore. Small galaxies, especially ultra-diffuse dwarfs, show rotation patterns that refuse to match any dark matter halo simulation. In some, stars orbit almost perfectly in line with their visible mass, as though hidden matter isn't there. Others show far stronger gravitational pulls than any plausible amount of dark matter could produce. It's like the universe uses different rules from place to place. You think astronomers could tweak their models, make the invisible halos puffier or more concentrated, to fix that. And they've tried. Yet each fix for one galaxy breaks another somewhere else. No single form of dark matter reproduces everything we observe. The invisible glue seems to shift its properties every time we look closer. Here's a striking example. The galaxies NGC 1052 DF2 and its twin DF4, discovered only a few years ago. When astronomers measured how their stars moved, they found something no one expected: motion completely explained by visible matter alone. Essentially, no detectable dark matter. At first, skeptics called it measurement error or tidal stripping, but other similar systems have since been found, too consistent to ignore. If dark matter is universal, how can entire galaxies simply not have it? On the flip side, telescope surveys also reveal companion galaxies with far too much apparent mass, objects whose gravitational behavior demands multiple times more dark matter than predicted. The halo models can't stretch that far without snapping logic. These contradictions were supposed to vanish with better data. Instead, they're multiplying. New missions like the James Webb Space Telescope made things even messier. JWST peers so deep that it effectively looks back in time to the first billion years after the Big Bang. In that early universe, galaxies should have been small, chaotic, clumpy, still assembling under the slow influence of dark matter. But JWST found massive, mature galaxies forming shockingly early, neat and structured. Simulations say there simply hasn't been enough time for dark matter to gather and form them by then. The same pattern appears in Euclid's first gravitational lensing surveys, clusters acting too gravitational, bending light more than visible mass plus modeled dark matter predicts. It's as though something amplifies gravity itself, a hint that maybe mass isn't the only game in town. Still, before we jump to rewriting physics, it's worth acknowledging why direct detection mattered so much. Until someone physically observes a dark matter particle, every inference remains indirect, traced from light curves, motion, and lensing distortions. Without a tangible detection, we can't know whether those signs point to hidden mass or flawed theory. That's why the scientific community placed its bets underground, hoping a single unmistakable collision would silence the skeptics. But after half a century of perfect silence, those skeptics are gaining ground. Some are younger scientists, unburdened by decades of investment. Others are veterans who simply can't reconcile their data anymore. A quiet shift is happening, a move from when we find dark matter to if. To grasp how deep this shift cuts, you have to picture the infrastructure behind the search. Deep underground detectors in South Dakota and Italy, shielded from cosmic rays by a kilometer of rock. Satellite observatories mapping cosmic gamma rays. Colliders like the Large Hadron Collider at CERN smashing protons together at near light speed, hoping the missing energy after collisions reveals hidden particles escaping detection. Each test ends the same way. Limits raised, possibilities narrowed, but no discovery. And as each door closes, theorists open new ones. Maybe dark matter interacts only with itself, so-called self-interacting dark matter. Maybe it forms bose, Einstein-like condensates on cosmic scales. Maybe it's not particulate at all, but rather a field, spreading continuously through space. These aren't minor variations. They're desperate mutations born from absence. The strangest part is that the more flexibility the theory gains, the less falsifiable it becomes. A model that can explain every outcome explains none definitively. That realization stings. Science progresses by theories that can be proven wrong. When a hypothesis stretches to fit any new data, it crosses an invisible line from physics into metaphysics. And yet throwing out dark matter outright feels premature, because the gravitational evidence remains. Galaxies do spin too fast. Light does bend too strongly. Galaxy clusters do show more gravitational binding than visible matter allows. Whatever the explanation, something unconventional is happening out there. The question is whether that something is matter we can't see or laws we don't yet understand. This is where modified gravity ideas begin to attract attention again.